Okay, so as being introduced, I'm Kanyana Tosumi from NICT Japan. And today my talk is on the title of how do space weather research and operation activities in Asia Oceania contribute to the world. So as you may know, the ionosphere is considered as an entrance to space. And the ionosphere is a region where ionized gas is high in the vicinity of about 300 kilometer altitude. If the Earth has a diameter about 1 meter, it means that the ionosphere is a spherical shell floating at about 3 centimeters from the surface of the Earth only. Okay, so if you can see this cartoon, so please consider that this area is ionosphere, and this blue shape here are plasma bubbles, which are ionospheric irregularities. Please be noted that this cartoon is not scaled to size. In modern society, so various communications are using radio wave. However, since the system was built without considering the effect of space weather, there is a danger that it will not be usable at the time of disturbances. And in particular, for Japan, it is facing an aging society. Automated work such as automatic driving and agriculture using drone will become important. Since this plasma bubble have a great influence on satellite positioning, it is necessary to appropriately remove the influence of plasma bubble. And regarding being established infrastructures, space weather is likely to become an important business, especially in ASEAN countries. Therefore, NICT tried to encourage and support ASEAN friends on space weather activity. So, ionosphere has many effects on radio propagation as illustrated in this slide. So let's start from the sun. When the solar flare occurs, the solar X-rays penetrate to the highly absorbing region. This region is called a D region. This sudden enhanced D region will cause a radio absorption. And if we go further to about 100 kilometer altitude, there is a E layer here sporadically appears. So we call it sporadic E. With the sporadic E, it causes the overpropagation of the radio signal for HF and VHF waves. And then the overpropagated signal will become the noise source of the undesired region. Sometimes sporadic E can cause a daytime scintillation in GPS signal as well. And then if we go further to the F region, there is a propagating delay during the quiet ionosphere like this. And during the disturbed ionosphere, we can be affected from the scintillation as well. So next, I would like to introduce the propagation delay. The radio wave propagates as a function of refractive index. So if we consider the last term here, we can say that the radio wave propagates as a function of electron density and the radio frequency. If you consider this left figure, this is the figure showing the ionospheric delay as a function of ionospheric total electron content or TEC. So you can see that as the TEC increase, the ionospheric delay also increase. And if we take particle density in global ionospheric map into account, so we can interpret that large ionospheric delay will happen around the two crests like this in low latitudes. And the two crests are called EIA. These two crests called EIA or equatorial ionization anomaly. Not shown here, but if we zoom in, we will see various scale structures of the ionosphere. And the ionosphere has a large day-to-day variability. And this is the most important. Ionosphere have a local characteristic. So it's the reason why we need to have ionospheric observation network expanded its coverage as large as possible. All right, next, I would like to introduce another ionospheric effects, that is scintillation. So ionospheric scintillations normally happen in low latitudes because of ionospheric irregularity like this. So when the wave from the satellite passing through the irregular ionosphere is called the scintillating in the amplitude and phase like this. And in the worst case scenario, so the wave signal become deteriorated and the quality drop. And in the worst case scenario, it's called a log off of the signal. It means we will lose the signal. So the main cause of the ionospheric scintillation in low latitude includes two types mainly. First, during the daytime, the sporadic E always be a source of the scintillation. But if we go to the nighttime, equatorial plasma bubble of EPB is always the source of this kind of scintillation. All right, here is the effect of scintillation on the geostationary meteorological satellites. So you can see the left figure. This left figure shows a normal image from satellite, but after 1 hour later, ionosphere become irregular and the received satellite signal become scintillated. As a result, as you can see, there are many lost strips like this. So it means we lost information. What happened? So it means this kind of effect could be critical if it was a time to monitor a super typhoon and capturing a supercell was missed, for example. All right, I have another example of scintillation effect on communication signal. So there was an excellent report that military officers could not catch an urgent message at the battlefield due to plasma bubble. So it means at that time it led to inestimable loss in 2002. So this is another effect from space to the military operation. So now I believe that you have already got some idea on how ionospheric monitoring is important in low latitude. And the suitable place for ionospheric network is a place that covers both geomagnetic northern and southern hemispheres. So there is limited land on the Earth, as you know. So from this map, you can see that only 3 areas, 1, 2, and 3 on the Earth are possible. First one here. For the first one, this is the Amazon jungle area. So it's quite dangerous. Then we can say that it's not suitable for ionospheric network. Second one is Brazilian region. There are many ionospheric observation equipment here. And the third one is Southeast Asia. That is a place that we have our network installed. So it means we own very unique observation network in the world. Since 2003, we have the Sea Lion network spread spreading in Southeast Asia like this. So previously it was operated in 4 countries, including Thailand, Indonesia, Vietnam, and Philippines. This is one of the unique observation networks in the world that cover both magnetic northern and southern hemispheres, where we can have a conjugate observation. But in addition to this, it is effective to use a VHF radar at the deep equator. So it means we will be able to know the exact position and shape of plasma bubble soon after it's generated. So in January this year, we have successfully constructed the VHF radar at the deep equator here. So I will show you in the next slide. But in addition to this, so we also collaborate with Ceylon friends to expand our network to other countries. So since 2019, we have successfully expanding our network from 4 countries to 6 countries. And the new 2 countries are Laos and Myanmar. All right, so as I mentioned before, we have installed the new VHF radar at Chumphon, Thailand. Why Chumphon? Chumphon is a place that is close to magnetic equator where plasma bubbles are expected to generate it. And it is the best place to observe plasma bubble from its initial generation state. As I showed before, in the vicinity of the plasma bubble, radio propagation are disturbed. So it means it may degrade satellite-based navigation and communication signal. And for this reason, continued observation of plasma bubble is strongly desired in recent years. And routine observation of plasma bubbles by this radar is expected to be a major advancement in expanding the use of precise satellite-based navigation in the field of agriculture, construction, and other. So for the new radar, we use the 18 Yagi antenna, and we install it as an array along geomagnetic east-west direction. And the VHF radar is operated at 39.65 megahertz with 25 kilohertz bandwidth, and the range of which can cover about 1,000 kilometers. So let's say the latitude can be covered up to 20 degrees in the north. All right, regarding the VHF radar installation, so we did a press conference and press release as well as the opening ceremony. So at the end of the day, we got 2 news broadcasting and 95 new published worldwide like this. So it means we gain interest from people worldwide about the plasma bubble activity. All right, last but not least, so we have an activity called OSWA, Asia Oceania Space Weather Alliance. So NICT established OSWA in 2010 to encourage the member countries to share information and to work together on space weather activity. Actually, the 6th OSWA workshop was scheduled to be held in Malaysia in August this year, but due to COVID pandemic, this workshop was also postponed. And recently, NICT as the SOC have been discussing to have an online workshop, just like the SPP. And the discussion theme will be slightly shifted from the pure space weather research and activity to be a lesson learned from COVID-19 and what is the step for the future plan for space weather research and operations, something like this. So the detail will be announced soon later. All right, so let me summarize my talk here. So NICT established and actively promote the space weather activities in Asia, Oceania. For example, you can see many activities like ASEAN IDO, Ceylon, and Australia. Sea-land network will help clarifying and removing the ionospheric effect on precise positioning system. And the precise positioning system will be an indispensable technology in the near future. And even with COVID-19 pandemics, NICT keep a close collaboration with partners by empowering ICT network to enhance and expand space weather activity. And that's all my talk. Thank you.
This morning, allow me to share my thoughts regarding developing durable physics competencies for the future of work. So my presentation this morning is actually divided into three major parts. First, I'll talk about how do we understand the future of work in terms of recent developments and in terms of changes in the landscape of work. Next, I'll talk about durable physics competencies by presenting to you some international frameworks on workforce readiness. And lastly, I'll talk about learning theories and pedagogies that will really help support the development of these durable physics competencies. So the main context that drives what you call recent changes in work that actually impacts education and also workforce development are two things. First, rapid digital transformations and an ongoing impetus for STEM skills for the economy all over the world. In 2017, ILO conducted a study regarding ASEAN in transformation and identified the skills that are most important. They identified technical knowledge as well as teamwork and communications. And they also identified that the skills most difficult to find are the following: strategic thinking and problem solving, technical knowledge, innovation, and creativity. From the World Economic Forum, I tried to map out the Futures of Jobs report that they did and look at the different listings of priority skills that they are looking for. So in the Philippines, for example, it's identified that 51% of the Philippine workforce would require reskilling, as opposed to Thailand with 51% and also Indonesia with 50%. If you look at the priority listing, at the topmost is analytical thinking and innovation, similar also to the other countries. We also have active learning and learning strategies, creativity, originality, and initiative. We also have technology design and programming, critical thinking, complex problem solving, systems analysis and evaluation, leadership and social influence, as well as emotional intelligence, reasoning, problem solving, and ideation. Unique to the Philippines is the 10th in the rank, which is resilience, stress tolerance, and flexibility. For a quick assessment of the list presented here, I would like to ask you this question. Are the skills listed here intuitive in physics education? Are they common or are they developed in our field, which is physics education? Yes, these skills are very much developed in our own field, which is physics ed. In 2018, there was a research regarding skills distribution in jobs, courses, and publications. Here, it's being shown in the first graph. It actually shows the centrality of skills as they occur in job advertisements, course syllabi, and research publications. Soft skills are rendered in orange, and hard skills are in purple. We see that across jobs, courses, and publications, soft skills like management are substantially more central than hard skills, meaning that they are more likely to co-occur with hard skills like optimization and data analysis than hard skills are to occur with each other. Nevertheless, soft skills are most central in jobs, somewhat less central in course syllabi, and much less central in research publications. Note especially how communication skills are critical to a wide variety of jobs, but are only mentioned in a few courses and research publications. This highlights a substantial discrepancy between how central soft skills are to the workplace, including in technical positions, but how peripheral they are to technical courses and publications. From the same work of Berner in 2018, here it's being shown the network of skills within job advertisements. Notable skills in this visualization are the following: writing, organizational skills, scheduling, problem solving, computer skills, teamwork, and collaboration. Intuitive here are the following connections: creativity and research, as well as problem solving and organizational skills. A recent study published by Reuters identified Asian countries with most number of innovative universities. By its sheer size, no, China led the list, but and then we also have South Korea, Japan, Hong Kong, and Singapore. But in terms of the top three most innovative universities, we have Seoul National University leading the way with 907 patents, of which 78.2% success rate of application, and you have a commercial impact of 38.7. Commercial impact is a measure of how basic research impacts commercial research. And as you can see here, KAIST, or the Korea Advanced Institute of Science and Technology, it also has what you call 79.4% success rate in terms of application of patents. And you have a commercial impact measuring to about 57.8. Third in the rank, you have POSTECH, and which has a 48.8 commercial impact. This data emphasizes what you call the connection between academe and the industry in driving innovation, in driving economic growth, and there should be an emphasis on what you call the synergy among what is being done in the university research and that of its impact on commercial research. If you look at the different international frameworks on work readiness, one notable framework comes from the MIT World Education Lab. The MIT JWEL came up with this human skills matrix they call HSX. And as you can see here, they identified 24 durable skills that workers need in order to thrive in today's rapidly evolving organizations. They categorized it into thinking, interacting, self-management, and even leading skills. What's unique about this particular matrix or this particular framework is the emphasis also on different forms of literacies, such as digital literacy, civic and cultural, organizational literacy, and financial literacy. There's also emphasis on comfort with ambiguity, growth mindset, and even relationship curation. On the side of Singapore, the Skills Future Singapore identified what you call critical core skills, supporting holistic development. And they divided it into three categories: thinking critically, interacting with others, staying relevant. Notable of which are probably something that's quite new to our ears would be the following: transdisciplinary thinking. You also have building inclusivity, customer orientation. You also have developing people and learning agility as well. On the side of the Philippines, the International Labor Organization, in partnership with TESDA, recently came up with this NAT model of STEM and TVET. This STEM and TVET model actually signifies a way for securing skills for the digital economy. Here, the analogy is actually a NAT being used to secure skills for digitization. So here we are seeing STEM competencies as the NAT that actually drives this securing of skills for the digital economy. There are 4 domains that we can see here in the NAT model: STEM knowledge, thinking skills, multiliteracies, and socio-emotional intelligence. As you can see here, there are a lot of overlaps with the previous frameworks that I have shown you, with the MIT JWEL Human Skills Matrix and that of the Skills Future Singapore Critical Core Skills. Just to elaborate further on the STEM skills and how do we really interpret them and what to look for to be able to identify these STEM skills. So here is a systems diagram of STEM skills and some of the keywords that you may associate with them. For example, you think of creativity in terms of fluency, flexibility, originality, and complexity. As you can also see here in this diagram, there is an overlap between systems thinking and complex problem solving, thinking about a big picture, thinking about a whole part understanding, looking at what you call interconnection and interrelation, and a lot of other related STEM skills in this picture. So just to further elaborate on major STEM skills and how they are actually very much relevant to physics education. So we have here creative thinking. If you talk about creative thinking, there are four major components. You have fluency, the number of ideas that you're able to generate. Flexibility is about the number of alternatives that you can offer, or different uses, or different ways of, let's say, approaching a problem. Originality is the novelty or uniqueness of an idea, and elaboration or complexity is the level of details that are being provided if you are conceptualizing a project or an idea. In terms of critical thinking, I'd like to lead you to these major indicators of critical thinking. I often hear educators talking about fostering critical thinking, but when you ask them how it's actually manifested in class, they cannot readily answer. So here we're seeing some keywords that we can link to critical thinking. If you ask your students to state their assumptions, to pose questions, to provide evidence, for example, to make a critical comment, judgment, okay, make a reflection, an evaluation, uh, articulate their reasoning. Those indicators are associated to what you call critical thinking. With respect to systems thinking, we see here an illustration of how we can actually think more of this STEM skill. So instead of looking at disconnection, we look at what you call interconnectedness, big picture, whole picture, looking at different patterns, different relationships, looking at synthesis rather than analysis, for example. But of course, I'm not saying that we should not analyze. There are certain aspects of learning that we need to apply analytical skills. But there are also certain aspects of learning for which we need what you call synthesis, a putting together of ideas to be able to interpret it holistically. There's also here we can see silos as opposed to emergence, isolations as opposed to relationships. Computational thinking is another thing that's being advanced in different frameworks. If you think about computational thinking, one would readily answer coding and programming. But computational thinking is so much more than coding and programming. There's what you call decomposition, breaking problem into parts. There's also pattern recognition, abstraction, removing unnecessary details and focusing on the more important data. Of course, you have modeling and simulation. You also have evaluation. And for the starters, for example, you have algorithms, which is basically a series of ordered steps taken to solve a problem. Here, probably I'm not discussing a lot about social emotional intelligence, but I'd like to highlight growth mindset. So if you're looking at this particular slide, probably you'd like to tell later on in the privately message me in the chat box to which do you actually feel affiliated, no? Are you exhibiting growth mindset or fixed mindset? So if you view challenges as opportunities, if you, for example, acknowledge and embrace your weakness and being able to learn how to give and receive constructive criticism, and even being able to be inspired by the success of others, those are indicators of what you call growth mindset. And growth mindset, as McKinsey Global Institute identified, that is actually a very fundamental skill because it's actually linked to what you call intentional learning. It sparks curiosity. It drives continuous learning, which is very much important into what you call reaching potential and even pushing boundaries all the way. It's not just lifelong, but it's still also considered as life-wide learning. So some theories to support the following STEM skills, to be able to develop them in our classes, for example. So we have constructivist theory, emphasizing on construction of new knowledge. So there's emphasis on discovery of concepts, hands-on explorations. You also have social development theory, leveraging on social interaction, expert guidance, and even peer collaboration. You have andragogy for adult learners. It should be task-oriented, problem-centered, relevant, more experiential. You also have connectivism, harnessing the analysis or the identification or recognition of patterns, connections, and interactions. As you can see here, I'm also emphasizing on neuroplasticity, which is the continuous changing and learning of brain, and also the scaffolding theory of aging and cognition, which encourages continuous learning that prevents natural neural decline. Some of the pedagogical approaches for the future of work are based on the learning theories and based on the STEM competencies I have previously mentioned. Problem-centered approach, project-based, inquiry-based, design-based, phenomenon-based, education for sustainable development, and even collaborative approach to learning. So some of the examples of strategies that can be implemented in class anchored on what you call cognitive principles are the following. So first, if we want, for example, or for people to learn new ideas, you have to provide them multiple representations. You have to use analogies and you have to use diverse modalities. Examples of which are here. So you have a graph, for example, you have physical representations, numerical, analytical representations, podcasts, videos, and even simulations. To support the cognitive principle of new ideas being meaningful can be made durable if they are actually relevant or timely. So you have to emphasize connections in class, contextualization, and even citizen science. Here I'm showing to you the PhilSA data project, space data, for which for if you want to encourage citizen science in your classes, analyzing the data that's being here and providing insights of a bigger community, then we are succeeding in making what you call relevant, meaningful learning in physics education. Also, another cognitive principle, students strengthen understanding of ideas when they are more actively engaged with content. So some of the things that we can actually, some of the strategies that we can use in our class, first and foremost, design thinking. Also, you may use reverse problem solving, for which you ask students to explain solutions rather than, just routinely providing solutions to the problems that you provide. Data analysis, debugging of codes, digital storytelling of what you call complex ideas, and even asking them to curate their learning, or evidence of learning, or even digital content creation such as wikis. I also highlighted here video annotation. On the average, Filipinos spend about 9 hours using social media, using videos for entertainment. But there is actually a way to level up the use of video by actually integrating questions in the videos that they are viewing. And this can be done using this application called Video Ant, so for video annotation. So earlier, I presented to you the PNAS results showing that there is a disconnect between the emphasis of skills in researches and publications as opposed to the emphasis, the skills that are being emphasized or needed by jobs. But here I'm showing to you that there's a reason actually to be optimistic. A recent professional development activity in the University of the Philippines surveyed the skill preference of STEM faculty. And here we are seeing that they are able to recognize the STEM skills that we were earlier mentioning about. So here we can see critical thinking, problem solving, analytical skills, data analysis, and other related skills. Also, in a recent training of Tibet, they identified priority STEM competencies. And as you can see, a lot of the words that that are reflected here are also related to the ones identified by STEM professors from the University of the Philippines. So you have creativity, problem solving, critical thinking, and innovation. So the durable physics competencies are very much belonging to what you call a larger umbrella of STEM competencies. So we emphasize on creative and inventive thinking, critical thinking. We also emphasize on what you call growth mindset, learning agility, communication, collaboration. So all of these are very much needed for the future of work. So in summary, to end my presentation, I talked about the context of the future of work that we can understand right now, some durable physics competencies from international frameworks, and the learning theories and pedagogies that can be done or applied in our classes to be able to really make our physics education relevant to the future of work. Thank you.